Phlebotomy, the drawing of blood, has been practiced for centuries and is still one of the most common invasive procedures in healthcare. Even though it's a well-developed technique, needle stick injuries, which expose healthcare workers to bloodborne pathogens, continue to be a significant hazard for hospital employees. Each year, in the USA, hospital-based healthcare workers sustain an estimated 384,000 needle stick injuries from needles and other sharp devices, or more than 1,000 injuries per day.
There is risk for infection, especially for those areas with scarce resource and widespread infectious diseases such as hepatitis B, hepatitis C, and HIV. According to WHO in 2003, there are approximately 40% of hepatitis B and hepatitis C infections in healthcare workers attributable to contaminated sharps. Because of that, lots of safety devices such as retractable lancets and retractable needles came out. However, using them can nearly double the cost per venipuncture. That is also the reason why there are still many hospitals in developing countries refuse to use safety devices when undertaking phlebotomy. Therefore, what if there is a reusable and cheap safety device which can make phlebotomy more efficient and safer? To achieve that, we come up with an idea, a portable automatic blood drawing device using vacuum extraction blood tubes.
In our design concept, there are two main parts of our device: imaging processing system and mechanic system. Imaging processing system, which finds the location of the vein of the patient's arm, capture the image of patient's arm under the infrared LED and process the image in the control panel. Then send the location of the vein to mechanic system.
Our mechanic system, which guides the needle to the insertion point, consists of a base, a robotic arm, and a control panel. The structure of the base is designed for the patient to put their arm on, and it links the control panel and the robotic arm together. Once it receives the location of the vein, the robotic arm will guide the needle to the insertion area. The laser beam will show out the insertion point for users' confirmation.
The design of our mechanism allows the needle to make small adjustments of the angle of insertion. The user can choose between automatic or manual insertion on the control panel. For automatic insertion, user is required to confirm the insertion on the control panel. For manual insertion, the control panel provides camera feed for manually inserting the needle and deciding the insertion depth on user's discretion. Numerous blood samples can be collected through only single venipuncture. Therefore, the user doesn't have to touch the needle and the vacuum tubes throughout the entire insertion process.
We are confident of making a prototype. By the calibration of the camera using chessboard, we can define the Cartesian coordinate of the patient's arm. The reduced hemoglobin in venous blood absorbs more of the incident infrared than the surrounding tissue, which allows us to see the vein beneath the skin. Hence, we can know the coordinate of the desired vein from the infrared image. Then, take advantage of C++ and Python on the Raspberry Pi in order to pass the packet to a microcontroller board called OpenCM to drive the motors and allow the user to manually insert the needle. We use SolidWorks to design our structure and for dynamic simulation, and then use 3D printer to make our prototype.
If we connect our device to the internet, we could allow the healthcare workers to remotely control the device and actually become an important part of a home telemedicine system. For those people, like chronic disease patients, who need routine blood tests don't have to travel all the way to the hospital for a single venipuncture. Because of the portability and lightweight of our device, with the help of drones, the blood samples from different patients can be sent to the hospital with a proper cooling system. Patient safety is always the biggest concern, but we think healthcare worker safety is just as important as patients. We hope that we could make healthcare workers become more safer with our blood drawing device and help more people in the world.